So in this lecture, we are going to take a look at the electrical events in pacemaker cells or autorhythmic cells. So there are two areas where autorhythmic cells are concentrated in the heart, and they are the SA node and the AV node. So you can see that here on this picture. So the SA node is located in the right atrium, and SA stands for sinoatrial, whereas the AV node, and AV stands for atrioventricular, is going to be located closer to where kind of all four of the chambers meet. Okay, both the SA node and the AV node contain autorhythmic cells that depolarize on a schedule, and therefore are capable of initiating the wave of action potentials that sweep through the rest of the myocardial cells and generate a contraction or a twitch. But the SA node tends to propagate action potentials faster than the AV node, and therefore the SA node tends to set the pace of the heart. And so the SA node should be the pacemaker of the heart. Now, there are certain types of disease states where the SA node and the AV node don't communicate correctly, and the AV node may be setting its own pace, in which case the AV node will usually set a heart rate of like closer to 40 to 60 beats per minute, where the SA node by itself has kind of a default rate of about 90 beats per minute. You don't need to know those numbers for my class. I'm simply saying that if you end up going into the cardiovascular realm in more detail, you'll probably learn about certain types of heart failure where the AV node becomes a pacemaker, and that's not a good thing. So for our purposes, we're going to kind of ignore the fact that the AV node can be a pacemaker, and we're going to focus on the SA node or the sinoatrial node, which should be setting the rate of the heart. So basically what happens is there's an action potential in the SA node that is automatically generated. And that's going to be the focus of most of today's lecture, is looking at how that action potential is generated. But let's just assume for a moment that an action potential is generated in the SA node. Then what happens is the depolarization from that action potential leaks through gap junctions and kind of sweeps over the atrial cells. And truth be told, there's actually kind of two ways that this happens. One is through gap junctions, and one is through specialized neurons called the internodal pathway. I don't focus on the internodal pathway. We're just going to assume that it's pretty much through gap junctions, so we get the sweeping of action potentials through these gap junctions in the atria, and that causes the atrial contraction. Then the AV node picks up the electrical event and propagates it down specialized neurons down to the ventricles, and then action potentials come up through the ventricles, causing the ventricular contractions. So that's all part of the cardiac cycle, and we're going to look at that in the next lecture in more detail. What I need you to understand at this point is that it is the initial depolarization from an action potential that occurs in the sinoatrial node or the SA node that starts the entire cardiac cycle. So if my sinoatrial node is depolarizing once per second, then my heartbeat is going once per second. In other words, atrial and ventricular contractions once per second, which means that my overall heartbeat or heart rate is going to be 60 beats per minute, right? 1 per second, 60 seconds in a minute, 60 beats per minute. If I want to increase my heart rate, then what I will do is I will cause that sinoatrial node to depolarize more frequently. Let's say my sinoatrial node sends an action potential every half a second. Then I'm going to have 120 cardiac cycles in 1 minute, or my heart rate will be 120 beats per minute. So you can see then that the rate at which the sinoatrial node propagates or generates action potentials is going to dictate your heart rate. So this picture looks at autorhythmic cells versus the contractile cells. And again, really all this is showing is that the electrical depolarization that occurs in the autorhythmic cells are going to propagate through gap junctions to all of the myocardium. Now, you might notice, based on this image, that this looks familiar, right? We've seen that tracing before for an action potential, but this looks kind of weird and new. And once again, we are going to be getting into a new action potential tracing. So the autorhythmic cells kind of run their own action potential. And in fact, there's really more than just an action potential going on in the autorhythmic cells. So the first thing I'm going to do is I'm going to show you the tracing. Then we're going to go ahead and map it out ourselves and go through the events that contribute to that tracing. And then finally, we'll take a look at factors that can modulate how often the action potential happens. So here's the tracing. I don't want you to write anything out yet. I simply just want you to look at it and see that, in fact, there seems to be a new pattern. You'll also notice, if you look down here, that the action potential does not seem to take up the entire tracing. In fact, and again, don't write this down yet, we'll put this all together. The action potential is only this section. The section that precedes it, the slope upwards, is referred to as the pacemaker potential. Now, what's going to be important here is that action potentials are all or nothing, right? That's something we've learned. So action potentials happen the same way every time. For the most part, and again, there's a little exception here, but we're not going to get into it. So for our purposes, this part of the tracing never changes. However, this part of the tracing does change and can change, and we'll talk about that. All right, before we get into that, let's go ahead and introduce our players. So we're going to go ahead and draw out the tracing, but before we do that, we're going to introduce the channel proteins that play a role here. And so go ahead and pause the video and copy this down if you'd like. So who are the characters in this action potential and pacemaker potential in autorhythmic cells? And so once again, we're going to introduce some new characters. I'm really not going to go into this in as much detail as I would have for some of the other action potentials. I'm really going to focus on the pacemaker potential because that is the part that changes, and therefore it's the part that we really need to have a good understanding. So, when we have learned about gated channels, we have learned about them in kind of a weird way. I have here a car wash sponge, and so you can see there's a hole there, right? There's my channel. If you assume that this is a membrane protein and this is a channel protein, there's the hole, right? And we've kind of learned about them like this. If they're a gated channel, there's a gate somewhere on there. And so in this case, the gate is closed, the gate is open. Gate is closed, gate is open. And that interpretation of how gated channels work has served us really well up until this point. Pretty easy, gate is open, ions pass through, gate is closed, no more ion movement. All right. There is another type of gated channel, and it is called an IF gate. Let me go ahead and write that down. And it is unlike anything we have seen so far. The I stands for current, and F stands for funny. And I'm not joking. That's actually what it stands for. Sometimes I make this stuff up to make it easier to remember, but actually it is funny current. It is our funny current gate. The funny current gate predominantly lets sodium through. So this is really a sodium channel. And it's not gated in a traditional sense. However, it can change its permeability. So going back to the prior example here, where we have our typical gated channel, no permeability, very permeable. No permeability, very permeable. You get the idea. So now let's take a look at these funny channels. I'm going to use my little car wash sponge here. I've got, I don't know if you guys can see it, but I've got actually holes both sides. So there's a hole that goes all the way through. And so you can kind of envision that in this way with the core, it's very permeable, right? So ions can go all the way through pretty easily. But now, what if I were to take this channel and start doing something like this? I were to start twisting it. Well, you could kind of imagine what would happen to the core, right? The core would start getting twisted and pinched. And so instead of having a nice, easy passageway all the way through, now suddenly it's like a corkscrew slide in there with pinch points. And it's a lot harder for ions to try to circumnavigate that passageway. So the IF gate is a twisty channel. It's not really a gated channel in our traditional sense. It's a twisty channel. And so when it's completely untwisted, it's very permeable, and sodium is allowed to move through very rapidly. But if I want to reduce the permeability, I start twisting it. Now it's a little harder for sodium to move. So in a given time period, not as much sodium will move. Now it's even harder for sodium to move, and once I've got it completely pinched off, no sodium will move. So hopefully that makes sense in terms of how this particular channel works. I have tried drawing this below. I'm not going to say I'm the world's greatest drawer here, but this drawing gives you an idea of what this channel might look like on the inside. So when it's completely straight up and down, completely untwisted, then sodium moves through very easily. And we expect a lot of sodium to be able to move in a short amount of time through one of those channels. As you start to twist it, it's a little harder for sodium to move in here because it kind of gets stuck at these pinch points. And it may eventually kind of swirl through, but not nearly as much sodium gets through. And then once you completely twist it, there's just no passageway, so nothing gets through. So what makes this particular channel protein so interesting is that it can exhibit various degrees of twist. The more twisted it is, the less permeable it is to sodium, and the longer it takes for sodium to come into the cell. And then if it's completely twisted shut, then no sodium comes into the cell. Interesting, huh? All right, so that's going to play a major role in our pacemaker potential. In addition, we have voltage-sensitive calcium gates. And voltage-sensitive calcium gates are going to start opening at about minus 45, minus 50 millivolts. And then we also have voltage-sensitive potassium gates. All right, I'm going to go ahead and draw a tracing. And this one's going to constitute probably about 0.8 seconds. Go ahead and draw this with me. So we're going to start with our pacemaker potential coming up to about there. And then we're going to go ahead and have our action potential. And our action potential kind of looks like this. And then the process repeats. So I'm going to go ahead and highlight my action potential in purple. The action potential is just that part of the tracing. The pacemaker potential, I'll go ahead and use in blue, a better blue. Okay, now let's go ahead and map our characters. So again, I'm going to spend most of my time talking about the pacemaker potential. But before I do, let me just very quickly go through what's going on in the actual action potential. So the depolarization part of the action potential is actually due to the voltage-sensitive calcium gates, which really start opening kind of back over here a little bit. So calcium influx, not sodium, but calcium, is what causes the depolarization. So this is unusual for us. we are used to seeing a rapid depolarization due to sodium influx. But here we're seeing a more gradual depolarization due to calcium influx. And then the potassium efflux is what causes the repolarization. So other than the fact that it's calcium and not sodium that's causing the depolarization, I don't really want you to know too many details about the action potential itself. We are instead going to focus on that pacemaker potential, because the pacemaker potential is super important. So the pacemaker potential is largely dictated by the funny gates. So the funny gates are going to let sodium in. Now sodium is going to cause depolarization. How we've learned about sodium depolarization so far is it's very rapid, right? It's just like shoots straight up. But here you're seeing a very gradual climb, which tells us not very much sodium is coming in, which tells us that the gates tend to kind of be twisted already. They're not super open. So they're already a little bit twisted, but sodium is still able to find its way in and cause a depolarization here. So from here to about here, we get sodium influx through the funny gates. Okay, so here's how the funny channels work. At minus 60, they kind of look like this. As sodium comes in and the membrane potential is going to start rising, the funny gates respond by starting to kind of clamp down and twist farther and farther and farther, which makes them less and less permeable. So what I just described should correspond to a depolarization where it's going up, up, and then it just kind of stops, right? But I'm showing you a very consistent pathward up. And that is because as the funny gates start to close, calcium gates start to open and kind of substitute the depolarization. So initially, the depolarization that we see is largely due to sodium. And I'm just going to kind of create a thickness of line to show how much sodium is coming in. So you can see it's tapering off, which tells you that as the membrane depolarizes, less and less sodium comes in. By the time you're at minus 40, the funny gates are completely closed. So funny gates are completely closed by minus 40. But the calcium gates started to open already. And so we get a little bit of calcium helping us in this area to finish the job. And then once we get to minus 40, all the calcium gates open. And again, I'm just showing you the thickness of my line to represent how much of that ion is coming into the cell. So you can see a little bit of calcium comes in the pacemaker potential, and then once we get to minus 40, and calcium comes in more readily, causing a steeper depolarization. Okay, so obviously you can see this is kind of a lot, especially when we compare this to neurons and we compare this to the action potentials that are occurring in the contractile cells, which are totally different than what you see here. The important thing to really focus on is going to be the pacemaker potential. So once again, the pacemaker potential is not an action potential and can be varied, as we will see. But the action potential pretty much runs the same way every time. Here is the book's description of the pacemaker potential and action potential. You can see here that it's pretty consistent with what I drew. Go ahead and linger and confirm that all of this makes sense. Okay, so now what we're going to do is talk about the fact that we can actually adjust our pacemaker potential. How the pacemaker potential is adjusted is going to be covered in a case study that we'll do live via Zoom. For this lecture, I simply want you to see the effect of what happens to the heart rate when we change the pacemaker potential. So I'm going to show you this very busy picture. And it takes a moment to get familiar with it. We are going to focus on the gray line here. So without any autonomic input, no sympathetic, no parasympathetic, the heart is just completely detached from the autonomic nervous system. The gray tracing is what you will see. This is the default setting for the sinoatrial node cells, those pacemaker cells. And so in this image, you can see that we have 1, 2, and 3 depolarizations. Those are going to correspond to 1, 2, and 3 cardiac cycles in the span of 2.4 seconds. Now, that's the gray line, that's the default. The red line is indicating how the autorhythmic cells will change under sympathetic stimulation, norepinephrine, epinephrine. And so let's go ahead and trace the red line. So hopefully you've noticed already that there are more depolarizations in the 2.4 seconds. There are 5. So under sympathetic stimulation, I'm going to have 1, 2, 3, 4, 5 cardiac cycles, and therefore I'm going to have 5 heartbeats in that same period of time. Now, also notice that the part of the tracing that is the action potential really doesn't change between the gray line and the red line. So just so that we're clear, the action potential is there and there. What changes is the pacemaker potential. So take a close look at the pacemaker potential under sympathetic stimulation. In what 2 ways does the pacemaker potential change compared to the default setting? Take a close look. So hopefully you can see that first of all, our starting point is closer to threshold. In other words, we don't have very far to go before we hit threshold. Secondly, the slope of the pacemaker potential is steeper. Under default, it looks like this, but now it looks like this. Both of those changes contribute to a shorter amount of time that the pacemaker potential takes before you have another depolarization from calcium. So you can see how adjusting the pacemaker potential can change the amount of time it takes for the pacemaker potential to reach minus 40 millivolts. Both sympathetic and parasympathetic nervous system can adjust the pacemaker potential. Let's look at the parasympathetic nervous system. The gray line here is the default. The blue line represents parasympathetic stimulation. So under parasympathetic stimulation, look at what's going on with the pacemaker potential. It's taking a longer time. Why? What 2 things have happened that make it take longer to reach the minus 40 millivolt threshold? So one thing you might notice is that we start our pacemaker potential in a more hyperpolarized state. So it's going to take longer to reach that threshold. And then the other thing you'll notice is that the slope is a little bit more shallow. Both of those contribute to a longer pacemaker potential and therefore fewer depolarizations and therefore a lower heart rate. So the sympathetic nervous system increases the heart rate by shortening the pacemaker potential, and the parasympathetic nervous decreases the heart rate by lengthening the pacemaker potential. So that's going to be where we'll end this lecture. In our next lecture, we'll take a look at the cardiac cycle in more detail, cardiac output, and an EKG. I'll see you then.